So our last presentation in this session is by George Chen from the Pacific Northwest National Lab. Now, it's kind of full circle for the whole day. We started with graph theory, and that put a lot of people to sleep. I'm thinking that this will wake you up, because this is, this is really good. George is going to talk about real-time graph pattern matching in their system called StreamWorks. I think you're going to find it very interesting.
Okay.
George.
Thank you. Okay, so I work with a team at PNNL in a program called the Center for Adaptive Supercomputing Software. And the aim of this group is to develop scalable graph algorithms to support cyber analytics. And so what I'm going to talk about today is one of the research prototypes that we're developing in this program called StreamWorks. Okay. And so the idea of this prototype is to be able to detect precursor events and patterns as they emerge in complex networks. And the idea here is that you can detect these things before timely enough so that you can mitigate or act upon them before they are fully realized. And so what we're trying to do with this research is to look at the evolution of critical graph patterns as they emerge, try to define an optimal search strategy to identify these emerging patterns. And we want to consider the cases where we have patterns that may or may not be known in advance. Now, as some of the earlier talks have discussed, subgraph matching, pattern matching, or isomorphism is an NP-hard problem. And there's been some limited work trying to do subgraph matching, but also in the context of a dynamic network where the network is changing and emerging, evolving over time. So, the algorithms that we're developing here can be applied in different areas. We're applying them to cyber attack detection, but other areas could be in social media analysis, stock market analysis, and distributed sensor networks. So, a little bit about the general approach. The idea here is that you start with a pattern, a graph pattern that describes a type of attack that might be occurring. We want to take this sort of attack, this pattern, and decompose it into smaller elements. What you do is just take a piece of this pattern, and you take it out of you essentially decompose it into smaller elements, and you successfully decompose it until you end up with a set of smaller elements to search for. And so just to give you an idea of how this might work, given that data comes in, we have a dynamic graph that's tracking the emergence of the different patterns. As one of the smaller patterns emerge first, you save that partial match. You continue looking at the data as it comes in until another smaller pattern matches. If those two patterns, the smaller patterns, link together based on some common edges or nodes, you can automatically move up and down what we call here is the join tree to essentially attach the smaller patterns into a larger pattern. So the essence of this capability is there's several things here that are important to look at. One is this idea that you have these smaller patterns, which are the first things at the leaves that are being looked at. If you can find these first, then you're trying to detect the precursor patterns, early patterns that might be indicative of this final pattern at top. What's also important here is from a computational standpoint. We know that subgraph matching is an expensive operation, but the exact matching is only occurring at the leaves with the smaller patterns. So you're not trying to do heavy graph computation on large patterns. You're doing it at the small patterns, and you're combining them in some trivial operation, right? And so this is, in a sense, what we're doing here is we're trading off space for speed. We're saving partial patterns for matching as it occurs, and we're only doing the matching, the actual computation for doing the exact subgraph matching only occurs for small patterns. Other thing here is to note is that these percentages we have here identify sort of the level of matching that's occurred. In this case, all we're showing is how much of overlap do we have in the primitive pattern compared to a larger pattern. But the better way to do it, and the better way that we are pushing, is this idea that you're actually training this join tree. Every time you're actually looking at the sample patterns as they occur over time on a stream, and you're collecting statistics on how often does this pattern occur when this attack actually occurs. So if you know that you're doing this based on evidence in the data as opposed to looking at the structure of the network. Okay, so here's what we're doing then. We're developing these subgraph pattern algorithms, and we package it together in a package called StreamWorks, where we're constructing a set of cyber attack graph patterns based on different kinds of attacks. And our initial work is working with some existing data, net flow data, the data that's coming out of San Diego supercomputing, known as from the Cooperation of Association for Internet Data Analysis, and also some simulated data from the New Brunswick Information Security Center. We are also in the process of getting some data from PNNL as well and trying to connect to a real-time stream at PNNL. Okay, so what does the pattern look like? So the whole idea is that you could have an attack represented as a graph. That's what we want to start with. And so this sort of attack, this is the Witty worm attack. This is part of the data set that came out of San Diego supercomputing. So the internet worm that began back in 2004, the sort of information that you might have in your graph is this idea that this attack is propagating across a series of hosts, and these hosts are sending out messages based on a certain port and with a certain packet length. So this sort of pattern is the sort of pattern you might want to be able to construct and apply in our system. Another one might be a distributed denial of service Smurf attack, where we have a hacker come in sending packets to a broadcast IP address, and that's sending a spoof source address. The address then could be an ICPM echo request to the host, to different intermediate hosts, which are then replying to the victim and flooding the victim. So again, this is sort of a graph pattern that we're looking for to decompose for our system. And finally, one more here is looking at distributed denial of service amplification attack, where you have a set of zombies or agents sending in spoofed addresses on DNS queries to different DNS servers. The servers are sending the query responses to the victim, but in this case, they're sending in the actual response packets are very large compared to the actual request. So it's flooding it with information and data. So given this, what we can do then is take one of the cyber attack patterns, and this is the Smurf attack. And again, we're decomposing this one into smaller elements. And if you want to look at this one, we're actually taking each time step that is occurring through this. So this is chronologically ordered and based on time. So there's one step here, there's a fan out here, fan in here, and these become your elements on the leaves of your tree. And so based on this, then you're looking at these sort of smaller patterns first, seeing if they emerge, and when they emerge, you can trivially combine them to form larger patterns. And so this is the notion of how this would work with a cyber attack pattern. Okay, and so we've also attached this to a little visualization with this. This is based on a toolkit, a graph toolkit called GEFI. We've implemented graphs, connected that to our join tree algorithm, where you can see then essentially as we move up and down the join tree, you can find the patterns that are occurring that relate to the different level of matching. Right? So the blue ones here represent these smaller patterns. Over time, these might merge into larger patterns, like the purple one, and then eventually you reach the target pattern, which is the green. So combined, this is a set of tools that are really bundled into two areas. One area is really defining the join tree. How do you, given the candidate pattern, how do you construct the join tree automatically? And that side of it, you have the graph pattern library, a set of statistics collection tools, and the actual subgraph join tree generation algorithms that we're developing. On the right side, then you have the actual execution or runtime system, where we have the key subgraph pattern matching algorithms. On top of that, we have stream processing to take the stream and aggregate and filter the data for the subpatterns that should go into the join tree. And then applying some simple visualizations to actually show you what's going on. And this is all based on a scalable graph library that's also being developed at PNNL for doing semantic graph searches and queries. Okay, so this project, the big emphasis of this project is on scalability and high performance computing. And so this is how we're actually parallelizing the code. So there's, when we actually, when the data comes in, we're actually generating a dynamic graph. The dynamic graph grows over time, and edges age out of it as well. So you have a certain time interval about for that dynamic graph. When we get a batch of new edges coming in, that represents an update graph. Okay, so the parallelization is dealing with the update graph and its relationship to the dynamic graph. And so the parallelization is occurring in different places. One place is that every time when you merge the update graph with the dynamic graph, that's all done in parallel with the edges and nodes. The comparison with the actual subgraph trees, so the idea that you have different patterns that you're actually looking for, and each one of these different patterns are represented in a subgraph join tree. And so you're searching through the nodes of the multiple subgraph join trees. So we're doing that also in parallel. And then the last part is that once we have found sort of the patterns in the update graph, we merge that with the patterns that's been found in the full graph. And so that merging is also done in parallel. So there's different stages of parallelization that's occurring with this algorithm. And so this is just some really preliminary information or scalability results. So here we have the Kata data. It's not the biggest one, but it's about 2.5 million nodes and about 20 million edges. We've laced it with a series of Smurf attacks, and just to see what the performance of trying to do the graph search against this data set is. And so we found that given on our high performance cluster of AMD cluster nodes, we're seeing some pretty reasonable scalability improvement in the processing time from 2 nodes to 16 nodes, right? So this is showing some scalability results in terms of the graph search algorithm. A little bit about the dynamic data structure we have. So again, this is all looking at a distributed computing. So the data, what you do is we have a pre-allocated array of edges, and these are stored across the memory of different nodes in our system. For this, we call this an edge pool, and in the edge pool, there's slots that are fixed size slots that are in the memory pool. And what we do then is for storing the dynamic array or dynamic data structure or the graph, what we have is a series of vertices here representing the host, and then essentially the edge list representing the different messages coming out of the host. This is a multi-level adjacency list, each of these conforming to different dynamically allocated slots that conform to the different links for all the edges that correspond to a particular a node. Okay, and so the nodes, the edges might overlap several slots as it goes through this memory pool, but it's all linked together using our multi-level adjacency list. Okay, so a little bit more here. And so we are conducting parallel searching across all the subgraph patterns. So given that, again, we have multiple subgraph join trees, we're looking at all the different patterns that are all the partial patterns that might be occurring in the full graph at the same time. Okay, we're doing that in parallel. In the future, we want to also leverage locality in terms of operations, so that if there's certain join trees that have similar nodes, we don't necessarily have to do, we can do that once instead of the multiple times that they appear in the nodes. Same thing with leveraging locality in terms of the data. So there might be certain spots in the network where we're looking for information against queries in the subgraph join tree. if we can just focus on the same area of the network for multiple searching, we can also optimize some time based on that. Okay. Stream processing too. So what we're doing in terms of the stream processing is that we're using Apache Storm, which is an open source stream processing system from Apache. You can use it to filter and aggregate NetFlow data. And then we're taking the filter data and passing it through a Apache ActiveMQ, which is an open source messaging system. And so there has to be some tuning that we're doing in terms of how we filter and aggregate data as opposed to how the size of the subgraphs that are actually in the subgraph join trees. So we're working with that at this point too, trying to figure out what should be aggregated versus what should be the size of those smaller patterns that are in the join tree. Some preliminary results on this. What we're seeing here, running 1 million NetFlow records through Storm at 1 record per message. We're seeing here is sort of the scalability, how many records can we process per Storm thread. And what we're seeing here is that with the red one here, we're actually seeing no filtering or no aggregation at all. The blue one here is with aggregation and filtering with 3 or 4 bolts. And you're actually seeing better performance with the aggregation and the filtering, actually using Storm to do the filtering. And so what this is telling us is that that I/O is the big issue, right? That it's in the case of no filtering at all, the amount of data coming out of the bolt is much higher than what after filtering and aggregation. And so so the I/O is more expensive than the actual computation involved in the filtering. On this side, we're showing some results based on how fast we can update the graph. And essentially, we're able to update the dynamic graph. If we do like a 10 million size batch, we're seeing scalability up to 16 nodes. If we do a 100 million size batch, we're just seeing scalability just up to 16 nodes as well. So what this implies is that the bottleneck for these algorithms are going to be more on the streaming side and the actual graph search side, whereas the update is going to be, we think that we're running out of work essentially after 16 nodes. So that's not going to be as much of an issue as the streaming and the graph search. Okay, now we've been working more heavily now with PNNL cyber security analysts trying to figure out how do we form these graphs. And one of the ideas here is that we look at all these graphs that I showed you before, and they're all based on NetFlow, trying to be able to look at the attributes of the NetFlow attack. But what we're hearing back from the analysts are that they're relying on a lot more information than just the NetFlow records. So the information that they also need to look at and draw these graph patterns, they want to know what, in terms of what hosts that the attacks are emanating from. For example, if this is just a port scan, we can depict the port scan as a graph. And we can easily encode that in our system and be able to search for that port scan. But it only has meaning when you actually delve further, right? And so this is where you might want to delve further. You want to look at the host where the port scan is being initiated, knowing what the type of server is that host. Is that host a known host? What is the machine type? Is that machine type known to be a scanning type of machine? You want to look at the user to see how many times has that user failed in logins, sort of its privileges, whether the privileges has been escalated. As the exploit occurs, there's other things that you want to look at is to be able to look at the applications that are actually propagating the exploit. Is it a known application creator? Is it a known process? Is it a known exploit? And again, as the exploit occurs, you also want to look at the users at that point too that are propagating that exploit, whether it's a new user and failed logins and so on. So we are in the midst of trying to fuse this NetFlow data with other streaming data sources, such as event logs, host scans, firewall logs, and anti-malware reports to identify more complex graphs to be able to search. And so part of this is then we have to enrich our semantic graph with a lot more attributes and to be able to fuse the data streams into a more rich data stream beyond the net flow information. And then again, build another suite of candidate graph patterns that has this fused information and attributes in it. Okay. I want to talk a little bit about the subgraph join tree generation algorithms that we also apply. So as we decompose the algorithm, decompose the graph into smaller bits, there's different ways that we can do that. So we've developed 3 different algorithms for doing that. And it's all based on how you traverse the graph from when it first starts to when it ends. Now, one simple way to do this is essentially follow the chronology of the graph, figuring out where things happen first, second, and third, and that essentially is following the breadth of the graph, applying a breadth-first algorithm to go through each step of the graph. Another way to do it is to look more at a depth-first approach, where you essentially follow all possible paths from the first to the ending condition. And so we also have an algorithm for doing depth-first traversal to generate your partial graphs. But the part that we find most interesting is this idea of doing a frequency-based composition. And so the approach here then would be to take your candidate graph and to identify all possible smaller subpatterns that might occur in that. And in this case, we're looking at subpatterns that are all dual-edge triads. Okay. And then using these patterns, then you train on it. You essentially look at the data stream and identify how frequent these smaller subpatterns are. Right. So what we have here is all dual-edge and single-edge patterns that can possibly come from that larger candidate graph. What you do then is essentially identify the dual-edge patterns that are less frequent, and you can continue finding the less frequent ones, and then you combine that into the next larger pattern. You continue looking, and as you do this, you look at how much of your full pattern that you filled out up here, and you try to identify what else can I put into this larger pattern to complete my graph. And then, but starting with the dual edge ones first, and then going down to the smaller ones as you move along. And so this is sort of the process that we are applying. And what this provides you is a frequency-based approach that will show you, that will provide you subpatterns that won't show up all the time, that are really discriminative of the larger pattern that you're trying to get at. And so that's our approach for automatic composition. Now, or automatic decomposition, that is. Now, the other thing here is that this sort of approach can also be applied to trying to look for unknown exploits. And so in this case, what we want to do is look at, for example, if you wanted to look at, in this case, you don't know what the pattern is ahead of time. You can look at dual edge triads that are centered around critical resources. So in this case, you might have critical resources at a particular file system or a particular database. And you want to look for all patterns in your traffic that relate to those critical resources. And then you start collecting statistics again. Okay, and so you want to find statistics on all the patterns that might emerge over time, do training on that. And then when you find patterns that are rare, and that you keep track of those, and when we have 2 patterns that are rare and they share a common border, share a common edge or node, then you essentially define the larger pattern based on that intersection. And you continue doing that, building up from these smaller patterns that are arising for those critical resources, right? Until you eventually, okay. until you can compose a full pattern based on that. And so really here then you're looking at statistics, a machine learning approach, trying to find infrequent patterns around critical resources that are infrequent based on what you've seen in the normal data stream. Okay, and you compose your patterns based on that. Okay, so in summary, this is what we're doing. Developing scalable emerging graph pattern algorithms to do this, to identify precursor events and patterns, using an efficient and novel subgraph join tree approach that tracks and monitors partial patterns and queries the graph against a large-scale dynamic network. We are applying this pattern matching algorithm to the detection of computer threats and intrusions, and packaging this all into a system called StreamWorks. We're currently extending this work to support multiple dynamic data sources, and also extending it to do the zero-day exploits based on the pattern, the frequencies of patterns that are occurring on the network. And that's it. So, thanks. Yeah, so you do. So, I mean, every time you find a pattern, then you're saving it as a partial match. And the idea there is that you want to save it so that just in case another pattern that connects to it is going to rise. But yeah, you can do that. But we also support the idea of aging, so you're not going to keep it forever, essentially. So if you set it for your window for a day, it's just going to stay there for a day. Right?
That can be used generally to develop this baseline behavior.
Right.
Without any real classification.
Right, and that's what we do in the zero-day exploit case. We essentially apply it, collect statistics on normal behavior about those smaller patterns that occur, and then for zero-day exploits, we find if are there any new patterns against the old patterns that are rare, and then that's when we then try to compose a new pattern as it occurs. So that's sort of the standard approach for just trying to understand the general behavior of a clean stream, right? Yeah.
So you mentioned that I/O was a problem as your kind of cluster size grew. Do you have any kind of intuition, kind of what the fundamental nature of that is? It the adjacency list blocking that the communication to search across your cluster gets too big beyond 16 nodes? And do you have any further intuition as to why that's kind of the bottleneck? And is there any relationship there between that and graph size? So if the graph size that you were searching for got kind of significantly larger, is there a possibility for better scaling as cluster size grew?
Yeah, and so I mean that's something that we need to evaluate. So we're doing the exact graph matching at the leaves, right? And so what we showed was just trying to do graph matching with two-edge triads. All right. Now you can imagine that doing the matching at the leaves for a larger size triad, larger size patterns at the leaves would be more expensive, but it might be more discriminative as well, because you have essentially you have a cluster or a subgraph that's more complex, and so that's one of the things that we'll have to measure to see are you going to gain the speed from the algorithm running fast, or are you going to gain the speed from having only rare occurrences showing up in the subgraph join tree, right? And so, yeah, that's something we'll have to essentially dig into a lot more.
And so I can envision where you can grow the graph that you're willing to match, and I/O will continue to be a problem, but you'll run into memory issues as you kind of increase those graph sizes with your adjacency graphs being distributed, right? And so it seems to me that there's probably an optimal point there where you're putting almost equal pressure on both your I/O and your memory. Would almost seem like it's the breaking point of taking the mechanism to its full fruition in current kind of technology terms.
Yeah.
Is that intuitively where you guys feel like you're pushing, or
Well, so that's something we have to find out, right? So there is going to be sort of the point where it makes more sense to, I guess any particular graph that you have, the selectivity is going to be a very important part of it, right? So anything that's going to match a lot, even in the partial matches a lot, we essentially have to store all that, right? And so we have to think about how selective it is, and how and how many partial matches we're going to get, right? And trying to balance the right querying against that, right?
Thanks.
Yeah. So. Thank you.